Good morning and welcome to this postgraduate video course on advanced hydrology. We are into the groundwater hydrology module, the last leg of this course. Yesterday we looked at the movement of groundwater in the saturated zone, and essentially we looked at the Darcy's law, its applicability and validity. And then we also looked at a numerical example in which we saw that how we can calculate the hydraulic conductivity and calculate certain other parameters like Darcy's flux and the actual velocity and so on. Today what I would like to do is like to go back a little bit and look at some more aquifer properties which we actually skipped. Okay. So, we will start looking at specific retention and the specific yield, right. So, how we define these parameters or these aquifer properties, which are important to understand as we will move along in this course and look at the movement of the groundwater in the saturated zone. This specific retention is denoted as S subscript R, okay. And let me give you the definition and then give you the expression of a soil or rock, and we are talking aquifer here, is the ratio of volume of water it retains after saturation against the force of gravity to its own volume or to its total volume. Okay. So, what it is basically what we are saying is that it is the ratio of the water retained by the soil against the force of gravity, means what, when the gravity forces are not there. So, water being retained by suction or some other forces, right, after the sample has been thoroughly drained due to the gravity forces, and to its total volume, right. So, if we define it, it will be S subscript R will be, let us say, V R over V T, and using the equation numbers, let me number this as 15, which we have been following, where V R is the volume occupied by retained water, it is the volume occupied by retained water, and thing to remember is that it cannot be drained by gravity. Or pumped out even. When we pump out, we cannot pump out the retained water, and V T, of course, we had defined earlier, it is the total or the bulk volume. Of the soil. So, this basically this parameter gives us some idea about how much water cannot be extracted, all right, and this retention power or the retention capacity of different types of soils will be different, all right. So, depending upon that, if we have some idea, we know how much water we are actually going to play with if we have an aquifer of certain volume available to us. The next one is the specific yield. It is very important, and this is denoted as S subscript Y of an aquifer or a soil or rock is the ratio of the volume of water that after saturation that after saturation can be drained by gravity, okay, to its own volume. That is the ratio. Okay. And this we can then write as V y over V t, that is the ratio. Let me number this equation as 16, and then V y is the volume of water drained or pumped out. Okay, right. So, this basically this specific yield gives us an idea about how much water is actually available. All right. So, there is a total pore space in the or the porosity. Out of this, certain fraction actually if it is saturated, certain fraction cannot be available for any useful purposes. Okay. And that is your specific retention, and the specific yield is something which can be pumped out or we can use. Let us see that or note that what will be the sum of this V r and V y, that is the sum of the water retained and the sum of the water drained from a sample or a saturated sample, volume of the voids, the total voids, right. And similarly, because if you divide this equation by V t, then you can say that the specific retention plus the specific yield will be equal to what? This obviously has to be equal to your porosity eta, yeah, that is let us say 18. Okay. Now, this S y is something important. It depends on what? Let me just list a few factors on which it will depend. It will depend on the grain size and shape, of the soil on which your eta actually depends, right, and also the distribution of the pores, how the voids or the pores are distributed, distribution of the pores, okay, how they are distributed with respect to space. How about the compaction? You may have an undisturbed sample and you may have a compacted sample, their porosity will be different and their specific yield obviously would be different. So, you have the compaction of the stratum, right. Also the time of drainage. Okay. If we keep pumping water, the specific yield will be changing as a function of time, all right, because the compaction characteristics may be different, okay, as a function of time. The next factor is the coarse or the fine grains, basically the soil type or the size of the soil basically. So, if you have the fine grains, means you will have little yield. Okay. Just final points we are looking at, and if we have the coarse grained soil, would mean what? You will have significant yield. Okay. Now, this yield will decrease with depth. Okay. As we have said earlier that the specific yield is will depend upon the compaction, and as we go down into the ground, the compaction due to the overburden will be increasing and the pore spaces will be decreasing. So, the specific yield also will decrease, all right. So, as we go down, the yield will be the function of the depth also. Okay. So, just to give you a few numbers, let me move to the next page actually. This S y is about 27% for coarse sand, okay, and it is about 3% for clay type of strata or an aquifer which consists of mainly clay, and this is about 44% for peat. Okay. So, you see that looking at the kind of aquifer the soil properties. So, we can carry out the borehole investigation, we know what kind of soils are present in the aquifer. So, once we have that, we get some pretty good idea about how much water can be tapped, all right, in the ground. Okay. For example, if we find that there is a coarse sand in the aquifer around a particular area, then we know the maximum yield we can have is about 25% or so, all right. But if it is a clay strata, there is hardly any yield we will have. So, there is no point spending money in exploring that particular area in which clay is present. Okay. All right. So, what I am going to do next is I would like to look at an example. Okay. Okay, third example in this chapter, in which we will look at this specific yield, how it can be useful in computing certain important things. And this is how it goes: estimate the average drawdown over an area where 25 million meter cubed of water was pumped from many uniformly distributed wells. The area which is extracted is about 150 square kilometers, and SY, the specific yield of that aquifer, is given to you as about 25%. Okay. So, looking at this, what kind of soil is this? It is some coarse sand. Okay. Okay. From the unconfined aquifer. This is an unconfined aquifer, and we are going to look at a little bit more closely what is this unconfined and confined aquifers. Okay. So, one thing which is to be noted here is what is given is to us is that we have an aerial extent of the aquifer. The aerial extent of the aquifer is about 150 square kilometers. So, it is a large area in which there are many tube wells which are dug, and we are pumping water. And what is said is, or what is given is that these dug wells or the pumping wells are distributed uniformly with respect to space. Okay. And this is an important assumption. Why? Because we can assume that the drawdown is uniform, all right, it is same everywhere. Okay. So, that is what we actually try to do, so that we do the pumping, the drawdowns are not very high at a concentrated location. So, these are the data given, and what we have to find is the average drawdown. So, if we have pumped out 25 million meter cubed of water, all right, in some certain duration, what will be the lowering of the water table, the groundwater table in this unconfined aquifer. Okay. A specific yield is given, and the amount of water which is pumped out, that is also given. Okay. So, let us see how we will do that. What is given to us is the volume of your water pumped out or drained. What is this? This is V y, we have just seen volume of water which is pumped is V y, and this is given to us as 25 million meter cube. So, I can say 25 10 6 meter cube. Okay. What is also given to you is the specific yield. All right, S y is 25%. So, it is 0.25. Okay. What is S y? Well, we have just seen it is V y over V t. Okay. So, this will give you the total volume of the aquifer. All right. V t would be what? It will be nothing but your V y over S y, is not it? So, it will be 25 10 6 over 0.25, okay, which will be 1 10 8 meter cubed. So, the total volume of your aquifer is 10 to the power 8 million meter cubed. Now, the average water drop average drawdown or the average water drop delta H, okay, over the whole area or the entire area will be equal to what? Will be equal to this total volume divided by the areal extent, isn't it? So, that will be equal to 1 10 to the power 8 over the area is 150 square kilometers. So, you multiply this by 10 to the power 6, this is meter cubed, this is square meters, all right. So, it will be about 0.67 meters. Okay. So, you say that the drawdown is about 0.67 meters or 67 centimeters. Okay. So, you see that we can calculate the average drawdown, but we had to find out first the total volume of the aquifer. So, and when we find the drawdown, we have to make sure that we are using the total area, not the volume of water, because that total volume of water actually is coming out from where? It is coming out of the whole volume, all right. So, water is actually stored only within the pores, and where are all those pores? Those pores are in the whole volume. So, you cannot just use the V y, you have to use V t. Okay. So, this is an important point in this problem. Okay. So, let us move on. The next thing we are going to look at is the concept of these different types of aquifer. Okay. The types of aquifers. Okay. We had very briefly said this that there are mainly two types, basically confined and unconfined aquifers, but we will say first we will look at unconfined, then we will look at confined, and then we will look at what is called leaky aquifer. So, we will look at these three types. Okay. All right. So, what is an unconfined aquifer? I think you are probably aware of these things. Okay. What is an unconfined aquifer? Well, it is the one in which the groundwater table is free, or it is not confined between confining layers. All right. So, you have a bottom layer which is an impermeable layer, and then you have the water surface or the groundwater table at atmospheric pressure, right, and these are shallow mainly in nature. Okay. So, you can define this as is one in which the groundwater table is undulating. Okay. It may vary from one place to the other in the form and slope depending on recharge. Okay. Because an unconfined aquifer can be recharged from the ground, okay, directly through the rainwater or the agriculture water or any other type of pond, and discharge pumpage from wells and permeability. Okay. So, an unconfined aquifer is one in which the groundwater table is undulating in form and slope depending on the recharge, the discharge, the pumpage, etc., and its permeability. Okay. The main thing is that the groundwater table is at atmospheric pressure in an unconfined aquifer. It is an important characteristic. Okay. The other one is that the rise and fall in the groundwater table, all right, correspond to change in storage. Change in storage in the aquifer. Okay. This is important. Why? Because when you have an unconfined aquifer, as we said, it can be recharged from the top, from the ground, all right. So, if there is any changes in the groundwater table, all right, if there is a rise, that means there is a change in storage or the storage is increasing, and if there is a fall in the groundwater table, that is a result of the change in storage, all right. So, the changes in storage or the rise and fall of the groundwater table is corresponding or related to the change in storage in a unconfined aquifer, and we will see later that this is not the case for the confined aquifer. That is why it is important to understand the difference. Okay. Now, the other thing is the contour maps or profile of the groundwater table in the whole aquifer, which is basically your water table in the wells, all right, observed wells. We can find such maps. So, these maps actually help in determining the quantities of water available. Okay, and its distribution and movement, and its distribution and movement. So, the important thing here what we are saying is that the contour map, if we want to develop a contour map in a unconfined aquifer or the profile of the groundwater table, then what do we do? Well, we just put some observation wells, all right, we dig some wells, you know, at some spacing, and then we observe the water table, all right. So, if we note down that water table, the elevation, and we develop some contour. What is a contour? Contour is basically line joining the equal elevation, all right. So, once we do this exercise, then that contour map is very useful in what? In, let me see, in determining the quantities of water available, because that will tell us how much water is available in certain area and its distribution, where it is concentrated and how it can move, all right. So, let us say if you have developed a contour map, okay, it may have a certain contour interval, okay, 1 meter here, 2 meters here, and so on. So, if you see the concentration of those contour lines which are very close in one area, means it is steeply sloping down. So, the movement will be very faster there, and if you have very flat gradients, then that is where you want to tap the water. Okay. Anyways, so this contour map is nothing but the water table in the observation wells, okay, in a unconfined aquifer, which actually will not be the case in the confined aquifer. It is a piezometric surface, slightly different, we will come to that little later. Before we move to that, I would like to briefly give you a concept of what is called a perched water bodies or perched aquifer. What is it? It is a special case of an unconfined aquifer. Okay. And what I will do is I will just give you a schematic of this before I give you the details of this. So, this is the impervious bed down at the bottom, impervious rock strata, and then you have the groundwater table somewhere here, all right. So, this is your unconfined aquifer, okay, and this is your groundwater table. Okay. So, what may happen is you may have some material, okay, which is impervious, okay, and there may be some water at a shallow depth lying in here. Okay. And these are called the perched water table, this one and this one. This we say is the perched water table, and these are some clay lenses, okay, some impervious material which is lying above the groundwater table, okay, and these are I would say impermeable strata, this one and this one. Okay. So, this perched water bodies basically they exist between what? The groundwater table and the ground level. Okay. This is the ground level, right. So, this is your ground level. Okay. So, it exists between groundwater table and the ground level. In zone of aeration, what is the zone of aeration? It is basically the unsaturated zone, all right, above the groundwater table. Due to relatively, how it is occurring? Due to relatively impermeable strata, of small aerial extent. Okay. So, it is very small, you see that some water may be available here, but it will not be much. It is usually shallow, as I said, the perched water bodies, and if you dig a well or the wells in a perched water body or aquifer, such wells will have what? Will have very small and temporary yields. Sometimes what happens is we start digging a pumping well, okay, and then what happens is we encounter certain water. So, we feel that we have reached the groundwater table, okay, and then we start pumping the water out. Okay. But after a few months maybe, or after some time, there is no water, because this was a perched water bodies and it is not the actual groundwater table, all right. And if you dig deep, it is very difficult to go through that clay strata. Okay. So, that is when we realize. So, whenever we are doing any investigation for water, we have to go sufficiently deep. Okay. Then continuing further, the example of such perched water bodies is the basically your clay lenses, as I just mentioned, clay lenses in the sedimentary deposits. Okay. So, this was about the unconfined aquifers. Now, we will move on and look at confined aquifers. Okay. They are also known as artesian wells, I am sure you may have heard these terms, or pressure aquifers. All right. These confined aquifers are called many different names. A few of them is artesian well. Artesian is basically coming from France. Some French hydraulic engineers, they carried out many investigations in the early 19th century, and they found out after they went very deep into the ground, they found the water, and the deep wells there are called artois, and the origin of this word is from that artois, which is a very deep well. So, it is an artesian well. Okay. And also it is known as the pressure well. Why? Because the water which is there in the confined aquifers is at higher pressure than atmospheric, it is at a very high pressure. Okay. That is why if you deep dig into it, water can come out very easily. Okay. So, let us look at this characteristic of a confined aquifer. As I said, the water is at pressure greater than atmospheric pressure. Okay. Second one is the water is sandwiched between two confining or impermeable rock or consolidated strata. Okay. The water level in any well which is dig into it will rise above the upper confining layer. Okay. Try to understand this. If we dig a well into a confined aquifer, the water level will rise above the upper confining layer. Why? Because water is at a higher pressure than atmospheric, it is just that it is confined. all right. In a well penetrating a confined aquifer. Okay. There are a few properties we are looking at of the confined aquifers. The water in the confined aquifers enters at regions. Where does the water come from in these confined aquifers? Well, it comes or it enters the regions where the confining bed, rises to the ground level, okay, because the water is sandwiched between two layers, all right. So, how does it enter into it? Okay. So, these confining layers somewhere have to meet the ground. Okay. So, when you have these two confining layers, there is some very far distances in certain region, it has to meet the ground, and that is where the recharge areas will come from. Normally, it may be the hilly areas also. Okay. So, many of the confined aquifers in Uttar Pradesh and the plains, the recharge area is coming from the Himalayas for Indian conditions. Okay. So, this is an important characteristic. When the confining bed ends inside the earth, okay. The earlier point what we said is the confining bed is going all the way up to the ground level, all right. In the second one we are saying the confining bed when it ends within the earth, okay. Then what happens? That means the confined aquifer actually becomes what? Unconfined. Okay. So, try to understand this. So, you have these two confining layers, all right. The recharge area we are saying is very far off in the regions where these confining layers will meet the ground, all right. However, if you have this upper confining layer, let us say it goes and then it disappears, all right. There is no strata or the confining strata ends here. After that what happens? Well, it becomes the unconfined aquifer. Okay. So, there can be all different types of possibilities. The recharge is from the recharge areas which are far off or leakage through the confining bed. Okay. As we have just said, the recharge in the confined aquifer is from very far off areas as compared to the unconfined aquifers, because in the unconfined aquifers the recharge can be from the top. Now, the important point I would like to make here is the rise and fall of the water level in penetrating wells. In the penetrating wells results in a confined aquifer we are talking about from changes in pressure rather than changes in storage volume. Okay. So, you have a confined aquifer. If you tap into it, all right, if you have a well inside a confined aquifer, you are drawing the water out. Okay. Where is this water coming out from? It is actually not the storage, all right. You have a recharge which is a continuous conduit, all right. So, this changes in the pressure which will take place, all right. So, there will be a very little changes in the storage volume in a confined aquifer. So, if there is a rise and fall in the piezometric surface, then they correspond to not the change in storage in the confined aquifer, but what? The change in the pressure. Okay. The pressure will go down, that is all. All right. So, let me reiterate that only small, very small changes in storage. Okay? And that basically means that these confined aquifers serve primarily as conduits for transmitting the water from the recharge areas. To natural or artificial discharge locations. So, I am going to say that this rise and fall, this point is important to understand, and also this last one. Okay. So, what we have said is that these confined aquifers basically serve as a conduit for transmitting the water. All right. How? They have a recharge area which is very far off. So, the water enters. If you pump the water out, there is hardly any change in storage, but you have the water getting started to move from the recharge area. And what is a discharge area? Discharge locations are what? Either it is artificial, in which you are pumping the water out, or it may be natural. Okay. From the confined aquifers, we have the phenomena which is called the springs, hot springs and so on. Okay. So, the confined aquifers are very much different as compared to the unconfined aquifers as far as their operation is concerned. Okay, because water is at a pressure which is higher than atmosphere. So, we have seen that the unconfined aquifers, we have the groundwater table at the atmospheric pressure. Now, in the case of the confined aquifers, if you dig a observation well into a confined aquifer, water will rise quite high. All right, and if you join the if you have many such observation wells, and if you join the points of the water levels in different observation wells, what is that surface called, or what is that line called? It is called the potentiometer surface, or the piezometric surface rather. Okay. So, that is what we will look at, the characteristics of a piezometric surface in a confined aquifer. Piezometric surface. We do not call it groundwater table because it is not at atmospheric pressure. It is also known as potentiometric surface. Potentiometric, it is a one word, I am just separating it, surface. Okay, of a confined aquifer is an imaginary surface. Remember, it is an imaginary surface. All right. Okay, it does not exist. Coinciding with the hydrostatic pressure level of the water, okay, in the confined aquifer. Okay. Okay. So, it is an imaginary surface which coincides with the hydrostatic pressure. As we said, in a confined aquifer, the water is at a higher pressure. So, the hydrostatic pressure may be higher than the atmospheric pressure. So, whatever it is, if you dig a observation well, the water will rise quite high. All right, and if you join that surface, that is called your piezometric surface. Okay. The water level in a well penetrating confined aquifer is what is equal to the elevation of your piezometric surface. That is what we are saying. Okay. The piezometric surface, may be below or above the ground level. Can you imagine that? You have a confined aquifer in which the water is at a very high pressure. If you dig a well, what may happen is that the water may rise above the ground. Okay, water will actually just ooze out. All right, it is called a flowing well, and we will look at these phenomena in a schematic diagram very shortly. If it is above the ground level, means what do we have? The phenomena is called the flowing wells. You do not have to actually pump the water if your piezometric surface is above the ground level, and we have springs. Okay. The contour maps say / profiles of the piezometric surface can be prepared from what? Water level data from the wells in a similar manner, as I just said. Okay. Because the water level in the well represents the pressure conditions. All right. So, if we can join them, we can develop what is called the contour maps in terms of the piezometric surface. If the piezometric surface falls below the upper confining layer, would mean what? Would mean that the water level will be at what? At atmospheric pressure, because it is connected to the recharge area. That would mean your confined aquifer actually becomes unconfined. Okay. Try to understand this. What we are saying is that if you have a confined aquifer in which the piezometric surface, if it is above the ground level, you have a flowing well, all right, or the springs. But if the piezometric surface drops below the upper confining layer, this is the upper confining layer, and if the piezometric surface drops below that, then what happens? Then this confined aquifer is no longer confined, because the water here is at the atmospheric pressure, because it is related to the atmosphere somewhere from the recharge area. Okay. So, then the confined aquifer actually becomes unconfined if the piezometric surface falls below the upper confining layer. Okay. The last point about them is that usually the unconfined aquifer occurs above a confined one. Okay. So, you have a confined aquifer which are deep at the bottom, and then on top of that you will have an unconfined aquifer. Okay. The next thing what I am going to look at is, I will look at an overall system in which I will show you all of these things. Okay. So, let us say this is your bottom confining layer. Okay. This is your impermeable strata. Okay. And then you have this is your ground. This is your ground level. Okay. And then you have, let us say, a well very deep into this confined aquifer. There may be another one down here. Okay. And then you have some upper confining layer like this. Okay. So, this is your some confining layer at the top. Okay. And I am not drawing this above, this is continuing here. Okay. So, this is your upper confining layer. Okay. And let me say that this is your confining bed. All right. So, what is this? This is your confined aquifer. Okay. So, if you are pumping water out from this, all right, we have dig this well from the top, then what will happen? The water will travel towards it, okay, from farther distances. Okay. All right. And then you say that you have the groundwater table, there is a unconfined aquifer somewhere down there. This is your groundwater table. Okay. So, what is this? This is unconfined aquifer. This is unconfined aquifer. Okay. What is this? This is obviously your recharge area, very far off, which is open to atmosphere. Okay. So, water can actually infiltrate into this and travel from long distances into this confined aquifer. Okay. And then it will go into this tube wells. All right. And then if I draw the piezometric surface, okay, let us say it is somewhere down here. It will be, let us say, horizontal here. I am saying it will cut here like this. So, this is your piezometric surface. What is a piezometric surface? If you have dig this well into the confined aquifer, so water level will rise up to this piezometric surface. So, this is your water level in this pumping well. All right. Now, this piezometric surface at this location in this particular well is higher than the ground. This is the ground, you see. All right. So, what will happen here? Because there is higher pressure, all right, then water will naturally start coming out. Okay. So, this is your what is called the flowing well or a spring. It may be natural, it may be artificial. This is the way I have shown, this is artificial, you have dug a well there, but then water will start oozing, okay, continuously. We can also tap into the unconfined aquifer. All right. So, this is a tube well dug into unconfined aquifer. Water will travel into this. Okay. You may also have some perched water bodies here, okay, some clay lenses. So, this is your perched. Okay. So, this way you see that we have looked at a schematic diagram in which we have tried to demonstrate how the confined aquifer will occur. All right. What could be the possible ways of the recharge areas? We can dig wells into a confined aquifer and then we may have either a flowing well in which water will be coming out automatically because the piezometric surface is higher, and then also we may have a penetration well in which the water table is not above the ground. All right. So, in that case we will have to pump the water out. All right. Nonetheless, if the observation well or the pumping well is deep enough, then water will come from the confined aquifers. We can also pump water from the unconfined aquifers. Okay. So, this is the different ways of looking at. Let me say that this figure is basically a sketch which is showing what unconfined and confined aquifers, okay, and how they occur, how they are recharged and so on. And obviously, this unconfined aquifer, how can it be recharged? Through rainfall. Okay. Water will go down and then it will recharge that area. Okay. So, let us quickly move on and look at the what is called the leaky aquifer. Okay. They are also known as semi confined aquifers. Okay. The confined and unconfined aquifers actually occur less frequently than the leaky aquifers. So, leaky aquifers are in fact more frequent. Okay. So, this is important to understand. When do they occur? Well, they occur when a permeable strata is overlain or underlain. So, either above or below, underlain by a what? By a semi pervious aquitard or semi confining layer. Okay. So, let us look at that. So, you have, let us say this is your impervious strata down at the bottom, okay, and then this is your ground level. Okay. Let us say you have a well very deep inside this confining layer, and then you have there is a semi confining layer. Okay. It is not exactly confining, but semi confining layer. Okay. So, this is what is called your leaky aquifer, okay, because it is leaking at the upper confining layer. So, it may receive water, all right, from the aquitard above. So, you have an aquitard, let us say, sitting above this. There is the water table which is down here. So, this is your groundwater table. So, it can receive water from the aquitard like this, okay, and one can tap into the leaky aquifer and then you will have water flowing like this. Okay. Now, this is important to understand that the pumping from a leaky aquifer removes water in two ways. Okay. How? One, horizontal flow, as I have shown within the leaky aquifer, which is what? Which is actually this one, okay. And two, or B, the vertical flow through aquitard, vertical flow through aquitard into the leaky aquifer. I have said here aquitard, but there can be an unconfined aquifer here also, which will contribute water vertically down into the leaky aquifer because of this existence of this semi confining layer. Okay. All right. So, these are the three different types of aquifers. Okay. Now, what we will do is we will look at what is called an idealized aquifer. So, these are the aquifers which actually occur naturally in the nature. All right. But when we are doing the modeling, when we want to model this, it is extremely complex. So, what we do is we try to idealize this, or we assume that they are homogeneous, isotropic and so on. There are lots of types of words I am going to throw at you. Okay. So, let us look at how we are actually or how we actually handle these situations, how we actually model this, all right, because it is a very heterogeneous system, it will be very difficult to model, all right. So, let us look at what is called the idealized aquifer. Okay. So, we are saying aquifers are heterogeneous and anisotropic. What is anisotropic? An anisotropic aquifer is one in which the aquifer properties vary in different directions. So, the mathematical modeling it is difficult. So, what we do is we idealize, or we use the idealized aquifer. Okay. As what? As homogeneous and isotropic. Okay. So, we are kind of disregarding those in most of the time. It is important to note that these such idealized aquifers, that is homogeneous, isotropic, etc., do not exist. Okay. They are nothing like an idealized aquifer which you will find in nature. All right. However, good or practical quantitative approximations can be obtained. Under such assumptions. Okay. So, we see that what we have done today is we have looked at some other aquifer properties in terms of the specific yield and specific retention, and then we looked up at an example, and then we looked at different types of aquifers and mainly confined and unconfined. There are various intricacies, the properties, and how they behave when they are subjected to either pumping or different types of forcing functions. So, all of this is important to understand, and towards the end we have seen what is an idealized aquifer. So, I think I would like to stop at this point of time, and in the next class we will look at how we can actually handle this anisotropic aquifers, okay, in which we may have different layers and how we can model that. So, I would like to stop at this point of time. Thank you.